In our subject selected topics in decision modeling, we are now at lecture 14 on integer linear programming. So, on integer linear programming, we have so far discussed how to formulate integer programming problems. A number of examples we have seen. Now, in this lecture, let us go to the solution methodology. So, there are different methods for solving integer programming problems, mainly integer linear programming problems, right. So, with regard to integer linear programming problems, the ILP problems, there are several methods. The first method that we shall discuss can be called as cutting plane method, is all right. The second method is a kind of enumeration technique, and there are two very important enumeration techniques we shall discuss. One is called exhaustive enumeration and the branch and bound technique, is all right. And finally, the heuristic methods. So, these are the methods that we shall discuss about solving integer programming problem. The first method, that is the cutting plane method, is like this, that first of all solve the problem by linear programming and cut the solution space in such a manner that all the integer solutions are preserved. So, what is this cutting plane method? Is that we have to solve an integer linear programming problem. So, first solve by linear programming method in the usual way, get the solution and then find out in that solution all sets of integer solutions, and find a clever method by which all those integer solutions are preserved, is all right. While you cut the solution space, you should cut minimally, your integer solutions are all intact and your solution space you are cutting minimally, so that the current optimal solution is outside your solution space. That means, you have already cut a certain portion of the solution space, the minimum portion where the current optimal solution is excluded. Then again solve the problem by linear programming and find the solution. If it is integer, the final optimal solution is obtained, and if it is not integer, then continue the process. So, this is a cutting plane method. The second method, the exhaustive enumeration, is systematically generate and evaluate all possible solutions and choose the solution with the optimum value, obviously the feasible ones. The problem here on the exhaustive enumeration is that if you try to find out all possible solutions of a given problem, the number could be very high. First of all, you have to generate them, you have to identify the solutions for them by some method, and finally see which one is the best out of all possible solutions. For a small problem, yes, exhaustive enumeration is a viable technique, but for large problems definitely not, is all right. So, the use of exhaustive enumeration as a method is highly limited. We shall not spend too much time on exhaustive enumeration technique. We shall rather move over to the other very important solution technique called the branch and bound method. You see, the branch and bound technique is a technique which breaks down the very large problem to smaller sub problems. But then there is a difference. See, we have solved dynamic programming problems in our initial lectures. We also divided a large problem into a series of sub problems, but those sub problems were different in the sense that a particular sub problem in dynamic programming was encompassing the entire problem. The next sub problem is taking out certain portion, next sub problem is taking out certain problems, certain portions, and they were all connected by a recursive relationship. This is not so in branch and bound. In branch and bound, the subsystems will be mutually exclusive but collectively exhaustive. Is all right? And once we are able to divide our total problem into such sub problems, and then we basically we generate branches, right. Each branch holds a sub problem. So, suppose original problem you divide into 3 sub problems, then initial branching will be 3, and then after then you should be having a method to generate a bound. Bound means the best possible solution. No, it is a minimization problem, it is a lower bound, and a maximization problem, a upper bound. So, those bounds should be possible to obtain, and then out of every n nodes you have to find what are the bound values, and from there it should be possible to obtain the optimal solution. Is all right? So, it is an involved technique, but very powerful technique which guarantees an optimal solution. In due course of time, we shall see the branch and bound technique. Lastly, the heuristic methods uses a specific heuristic methods for a class of integer problems. Mostly we shall discuss the travelling salesman problems for heuristic methods. Please also understand the meta heuristics such as genetic algorithm. They are all heuristic methods definitely, but we shall not discuss those problems here because we have a completely separate set of lectures on meta heuristics, right. So, apart from those evolutionary computing things, other heuristic methods we shall discuss in due course of time, right. So, these are the methods that we shall discuss for solving integer programming problem. Let us now go ahead with the first one, that is the cutting plane method, but before even cutting plane method, let us do a little revision on the linear programming itself, right. Let us take a very simple linear programming problem. A linear programming problem takes a form, as you can see here, the maximize z, let us say with 2 unknowns x1 and x2 is a function, let us say 40 x1 plus 50 x2 subject to, let us say 2 constraints, x1 plus 2 x2 less than equal to 40, 4 x1 plus 3 x2 less than equal to 120, and x1 and x2 greater than equal to 0. The integer linear programming for the same problem is an additional constant that x1 and x2 are integers. Now, a point to be made here, look here, the linear programming problems are mostly solved by the simplex algorithm. Before even understanding simplex solution method, a quick review, you see most of these problems that we shall discuss should be possible to solve graphically as well. But you must remember that you cannot solve all linear programming problems graphically. 2 by 2, yes, 2 variable problems, 3 variable problems you can still think of, but more than 3 variables it becomes almost impossible, really impossible to solve through graphical techniques, right. So, in such situations the simplex remains the only way possible. So, in the future courses, future course of action where I am going to show you a number of graphical solution methods, please remember I am also going to show you the simplex solution of the same. The graphical part is for understanding. For larger problems, the graphical solution is excluded. The reason is very simple, more than 3 by 3, that is more than 3 unknowns, the graphical solution is not possible. Is all right? So, in that case simplex remains the only solution method apart from other techniques like branch and bound and so on. So, the graphical method, if we have to solve this problem, then what we do really, we find out the solution space of this problem, but by drawing the constraints, right. By drawing the constraints. How do we draw the constraints are in this manner, that is, the first one, that is the x1 plus 2x2 less than equal to 40. So, what we do, you see this constraint line which is from 20 to 40, we draw a line, and as we draw this line is drawn from, let us say, if x2 equal to 0, then x1 is 40, and x2 equal to 0, then x1 equal to 20. So, a constraint line is drawn. Now, if I put 0 0, it is satisfied. So, 0, that means the origin is included, that means all the portions below this line within the x1 and x2 axis is covered by this constraint. Similarly, the other constraints, that is 4x1 plus 3x2 less than equal to 120 is also drawn, and all these area r plus s, that is covered in this particular constraint 4x1 plus 3x2 less than equal to 120, and this line represents 4x1 plus 3x2 equal to 120. So, the shaded area is then becomes our solution space, is all right, that is our solution space. Now, a beautiful understanding that we have about linear programming is that the optimal solution can be found out from one of the basic feasible solutions. What are the basic feasible solutions? Those are the corner points of this solution space, right. So, these are the feasible corner point solutions, that is 0 0, 0 20, 30 0, and this point where the two lines cut each other. Then what we do? We find out the objective function value at these 4 points, and then the point that returns the highest possible value is our optimal solution. Is it all right? So, that is how we can solve optimal such linear programming problems graphically. So, but then understanding of linear programming problem requires the understanding of the assumptions. What are the assumptions? The first assumptions, the objective function and the constraints are linear, that is the first. That means, all these constraints, there should not be higher order terms. For example, it should not be x1 square plus 2x2 less than equal to 40. If you have higher order terms, then they are not linear. You cannot represent them by straight lines, and if you cannot represent the constraint lines by straight lines, then the fundamental thing that one of the corner points, the feasible corner points will be optimal, that will not be valid. See, even if let us say the individual constraints are all linear and you get a solution space, but if the objective function is not linear, then also these will not happen. So, that means the objective function should be linear, the constraints should also be linear. That is the basic requirements of linear programming problems. All the constraints should be linear and all the objective function should also be linear. Continuity assumption. The variables can take on any value within a given feasible range, right. So, supposing what is the feasible range of x1 and x2 values. So, here you see the x1 value could be anywhere between 0 to 40, but feasible range is 0 to 30, right. So, that means while x1 feasible range is 0 to 30, x2 feasible range is 0 to 20, and any value within that is should be possible, say 10.2 should be possible, right, 0.9 should be possible. But then obviously they are not corner points. So, we shall not consider them, but theoretically yes, the continuity assumption said that the solution has no restriction for x to have any value between 0 to 30 in this particular case, that could be a possible solution. So, that is the continuity assumption. The third one, the additivity. There are no interactions between the decision variables. That means that we can add the x1 plus x2. Sometimes what happens, cannot add apples and oranges, is it not? But in this case, the constraints are written in such a way that you can, let us say if a resource is 40, then we can add certain portion of x1 and certain portion from x2, right. So, this should be possible. That is the essential idea of additivity. And then constant returns to scale. The objective function and the constraints exhibit constants return to scale. What does it mean? Is that you see, supposing I have a particular profit for x1, let us say 40, is it okay? For one item it is 40, for two item it becomes 80, for 3 items 120, 4 items 140, that is a constant returns to scale. If it is not, sometimes you see in realistically one item need not give you a profit of 40, maybe a profit of 20, but if you have 2 item or 3 item or more item, maybe you can make more profit. Or in a different place, maybe for one item you can have more profit, but 2 items you give a discount and then you reduce your profit. So, the constant returns to scale may not be true in certain situations, but if that is so, then linear programming assumptions will not hold. It is all right. Lastly, the finiteness, the parameter values must be known with certainty, right. So, that is finiteness. Now, tell me, if I translate a linear programming problem to an integer linear programming problem, which of these assumptions will not hold? Think over. It should be the continuity assumption. The variables can take any value within a given feasible range. This is not going to hold, right. The continuity assumptions will not hold, because the variable will not be able to take any value within the given feasible range. It will take only the integer values, is all right. So, that is the essential idea of an the integer linear programming problem. The continuity assumption will not hold. Now, let us see how to solve linear programming problem by simplex algorithm. So, we took a very simple problem, the same one. So, what we do, from the original problem we write an augmented problem. What is that augmented problem? We take 2 more variables because they are all less than equal to. So, we take that, actually these signs should be equal to, they are not less than equal to, they should be equal to. So, the augmented problem then 40 x 1 plus 50 x 2 plus 0 x 3 plus 0 x 4 subject to x 1 plus 2 x 2 plus x 3 equal to 40, 4 x 1 plus 3 x 2 plus x 4 equal to 120, and x 1, x 2, x 3, x 4 less than equal to 0. And then we put x 3 and x 4, the the variables which forms an unity matrix. You see x 3, x 4, they form an unity matrix, they become the basis and the values are 40 and 120 what we have there. And then we write, look here, there is unity matrix is here with the slack variables and the coefficients we write, and we write Cj minus Zj values. You see that Ci values, that means the 0 and 0, they are profits associated with x 3 and x 4, and 40 and 50 profit associated with x 1 and x 2. So, the total cost of making 1 unit of x 1 will be, you give away 1 unit of x 3 and 4 unit of x 4 at a cost of 1 into 0 plus 4 into 0. So, 0 cost, 40 is your per unit profit. So, Cj minus Zj is the net profit per unit of x 1 is 40, and 50 is the net profit per unit of x2, right. So, this is how we write the first simplex table. So, once we write the first simplex table, then from the first simplex table we find that out of x3 and x4 which one becomes a bottleneck resource. Look here, we have more profit from x2. So, x2 becomes our entering variable, and which one is the leaving variable? With x2 requires 2 units of x3 and 3 units of x4, is all right. So, with 40 units of x3 available, we can make 20 units of x2, but with 120 units of x4 available, we can make 40 units of x2. But can we make 40? Because we need both x3 and x4. So, which one is the bottleneck resource? The bottleneck resource will be x3 here. Why? Because if we make 20 units of x2, I require 40 units of x3 and 60 units of x4, which I have. But if I make 40 units of x2, then I will need 120 units of x4, which I have, but 80 units of x3, which I do not have. So, this means we can only make 20 units of x2. So, that is how we fulfill this table, that this should be 20, that is 40 divided by 2 is 20, right. So, it should be 20, 2 divided by 2, that is the key element. So, it become half 1, and then this becomes 1, this 1 will become half, this 2 will become 1, this 1 will become half, this 0 will become 0. For the remaining units, there is a simple formula. What is that formula? This 120 will become 120 minus 40 into 3 divided by 2. Is it all right? So, you just look at these highlighted areas. So, 120 minus 40 into 3 by 2, that is 60. So, that is how this 60 is filled up. Like this we fill up all these variables. So, this 4 will become 4 minus 1 into 3 by 2. So, 5 by 2. And since now x2 has come in the basis, these remaining values will be 0. Is all right? So, like this we fulfill this table and we get the simplex table 2, right. And then from there we obtain the simplex table 3, by suitably transforming these variables. Now, again x4 becomes the bottleneck resource. So, x4 is now the leaving variable and x1 will be now the entering variable. So, what will be the value? X1 will be 60 by 5 by 2, 24, and x1 20 minus 60 into half by 5 by 2 equal to 8. So, x1 equal to 24 and x2 equal to 8, that is our final solution, because look here, it is a maximization problem. X1 and x2 are in the basis. So, obviously, their Cj minus Zj value should be 0, and x3 and x4 they are not in basis. So, they are all minus. So, once we have all negative Cj minus Zj, that means the optimal solution is obtained, and the optimal solution is x1 star equal to 24, x2 star equal to 8. So, what will be our Z value? Z value will be 1360, and this is indicated here also. So, this point is our optimal value, right. So, I am sure that I have gone hurriedly about explaining the linear programming, but that is not our real purpose here. I am sure you know linear programming, but in case you have some difficulty, you can see maybe the beginners lecture, where we have discussed a little bit on how to solve linear programming in more detail, right. So, once we know how to solve linear programming problem, one thing should be understood, IP versus LP solutions, how do they compare? Suppose in a product mix problem, the LP solution is 0, then we can take 0 as the product 1. If LP solutions in integer, there is no problem, but if LP solutions is something like 825.8065 or 3261.935 or 867.0967. Look, these are very high numbers, So, a simple rounding off to 825, 3261 and 867 should not pose much of a problem, is all right. So, the very simple thing, that is rounding off, should be possible in many situations. So, where the number involved are large enough for a rounding off to be meaningful, we can definitely use the LP solution as our IP solution, right. So, if your LP solutions asks you to produce 1034.23 bags, you may not go too wrong if you produce 1034. What about 11.64 Boeing airplanes? Look here, it is very difficult then, because 11 Boeing airplane and 12 Boeing airplanes obviously makes a lot of difference, is all right. So, every situation is not same. So, we have to be careful which is the solution what we get here. Look here, rounding LP solution to integer problem, suppose this is our solution space and this is our LP optimum and this is our IP optimum, this is the integer solution. The LP and IP, they are very near, and as you move this side, objective function value increases. So, it is clear that since there is no other integer solution in sight and this side is our profit is increasing, all nearby integer solutions are worse than this, is it all right. So, we can say yes, this is IP optimum, we accept it, there should not be too much of a difficulty. But look here, look at this particular solution space. See, the LP optimum is here and IP optimum is somewhere here. There are so many IP solutions, integer solutions nearby, but non-feasible. See, if the solution space is visible, if you could draw a graph, obviously your understanding is okay. But suppose you really cannot draw the graph, you are solving by simplex, how do you know exactly which one is feasible, which one is not feasible? Difficult to know also. So, under such situations, rounding off, if you round off this value, you get either this or this, or this or this or anything nearby, they are not at all feasible, right. So, you cannot round off and get from LP optimum to IP optimum as you have done here. Look, if you round off this, you get this, there is no problem. But here, if you round off this, you do not get this, right. So, it is not that rounding off works all the time, is all right. So, it is not rounding off does not all the time. If you have particularly pointed feasible region, if you use LP to predict the solution for an IP where variables can have only 0, 1 value, typically in take leave situations, you cannot really use rounding off. So, it is not that you really can use rounding off in every situation, you have to use your discretion and see what can work where, is all right. Let us now look at this particular problem. Now, solve the following integer linear programming problem, right. Maximize z equal to 2x1 plus x2 subject to 2x1 plus 5x2 less than equal to 17, 3x1 plus 2x2 less than equal to 10, x1 and x2 are 0 greater than equal to 0 and they are all integers. So, how do you really go ahead with this problem? So, as you have guessed it right, first we solve a linear programming solution. The linear programming solution will act as our initial solution. If we are lucky, we get an optimum solution there itself, then we stop there. But if we do not, then we have to really see how exactly we can transform these LP solutions, and slowly we can obtain by cutting off the solution space an integer solution, right. So, we will take up this example in detail and we shall solve in our next lecture, right. So, thank you very much.